Is my screen visible?
Yes, sir.
Great. What is written there?
Solubility of drugs.
Great. So in the last class, we have started with states of matters, and I think we have covered solid state, and then we were supposed to move to liquid state, gaseous state, and liquid crystalline state today. But I think before moving to liquid state, we need to study about solubility of drugs because it is very much associated with that topic, and a thorough understanding regarding the solubility of drug is very important, and it would be helpful for your further understanding, because in the further phases of physical pharmacy also, and also for pharmaceutical technology, biopharmaceutics, whatever subject we will go through, the concept of solubility is very important. And also for your higher study, for your professional life, this is a very important concept what you will require in each and every steps. Also, a lot of questions come in GPAT examination or NIPER JEE examination or any other pharma entrance examination uh, from this topic. It's a very much popular topic to the question setters. And yes, so should I begin, or should we wait a couple of minutes for the others to join? Yes, yes. So Gaurav Gadai, you were trying to tell something. Okay, okay, okay.
Let's start.
Let us start. Let us start. Okay. So solubility of drugs. This topic has two module, module 1 and module 2. In module 2, we will go through some advanced aspects, and I will cover both of these module in today's class. So is my screen visible? I have just changed the screen.
No, sir, it's not visible.
It is not visible.
Sir, visible, sir.
It is visible. Okay. So whoever is telling the screen is not visible, check with your network connectivity, maybe. And when when my screen will not be visible, you will shout and raise your hand and tell me. Okay. So let us first know what is solubility. This is something what you should know. This is a very important concept. And at 1 minute, just I heard something. Someone wants to join. Saudu Kundar. Call your friends and tell, because when I will start discussing the topics, probably I will not I will not see the Google Meets window, so that will be difficult for the others who wants to join, and I will not be able to make them connected. Okay, let me start. So let us begin with the definition of solubility. Basically, it has two aspects. One is qualitative approach, another one is quantitative approach. So just go through the definition of qualitative approach. The solubility of a substance is the amount of it that passes into solution when equilibrium is established between the solute in solution and the excess or undissolved substance. Okay, so what can you understand from this sentence? Just tell me. Otherwise, I know you will not uh, respond by yourself, so I will ask by names. Uh, so yes, let me see the list. Um, Arnab Seal, yes. Tell me, what have you understood from this definition? Hello, Arnab.
Sir, definition of solubility.
No, I have written here what is qualitative approach of solubility, and it's a very important statement. What have you understood from that?
Sir, the solubility of the substance is the amount that passes into solution. Means that
Just don't read the line. If you are not comfortable in English, you can also respond in Bengali. I don't have any issue with the language. Okay, I have issues with the concept.
স্যার এটা মানে হচ্ছে যে সলিউট আর সলভেন্টের মধ্যে যে একটা ইকুইলিব্রিয়াম এটার দ্বারা স্যার সৃষ্টি হবে, মানে
Basically,
সলিউট আর সলভেন্টের মধ্যে সমানতাটা সৃষ্টি হবে এটার দ্বারা।
okay. So let us hear from some other students. Madhu Prasad. Yes, Madhu Prasad. Hello.
Yes, sir.
Yes, what have you understood from that definition?
So the concentration of the solute is saturated means, sir.
No. I am talking about qualitative aspect. You are talking about quantitative aspect. Please follow the class. Okay. So what have you understood from the qualitative aspect of solubility?
The solute is present in the solvent, sir, in the homogeneous mixture.
Homogeneous mixture, no, this is not something what is very true, because see, homogeneous or heterogeneous, this is a concept of phase, and phase is something different. Okay, so let us move to another student. What about Saurav Godai? Yes, you tell. What have you understood from solubility? See, let me share a story. জাস্ট ইমাজিন, আমাদের কাছে একটা, আমি বাংলাতে কনসেপ্টটা বোঝাই, তারপর আবার ইংলিশে ফিরে যাবো। একটা বিকার আছে, সেই বিকারে কিছু কোনো একটা সলভেন্ট আছে, মেবি ওয়াটার, মেবি জল। আমরা যখন ওখানে এক্সেস অ্যামাউন্ট অফ সলিউট অ্যাড করছি, এক্সেস অ্যামাউন্ট অফ সলিউট, ওকে, উই ডোন্ট নো হোয়াট ইজ সলিবিলিটি, কতটা যাবে কি যাবে আমরা কিছু জানি না, আমরা এক্সেস অ্যামাউন্ট অফ সলিউট অ্যাড করেছি। ইনিশিয়ালি কি হবে, ওখানে একটা কনসেন্ট্রেশন গ্রেডিয়েন্ট তৈরি হবে, যে সলিউটটা আছে সেখানে সলিউটের কনসেন্ট্রেশনটা বেশি, বাল্ক অফ দ্য মিডিয়াম দ্যাট ইজ সলভেন্ট, সেখানে সলিউটের কনসেন্ট্রেশন নেই। তাহলে কনসেন্ট্রেশন গ্রেডিয়েন্ট তৈরি হলে একটা ফিজিক্যাল ডেফিনেশন আছে যাকে বলে ডিফিউশন। ওকে, ডিফিউশন অসমোসিস, এই দুটো ফেনোমেনা তোমাদের ভালো করে জানতে হবে। ডিফিউশন মানে যখন কোনো কনসেন্ট্রেশন গ্রেডিয়েন্ট তৈরি হয়, তখন কোনো মেটেরিয়াল সেটা হায়ার কনসেন্ট্রেশন গ্রেডিয়েন্ট থেকে লোয়ার কনসেন্ট্রেশন গ্রেডিয়েন্টস এর দিকে মুভ করে। তাহলে মুভ করে কি করবে, একটা চেষ্টা করবে কনসেন্ট্রেশনে সাম্যতা আনার, ইকুয়ালিটি আনার। ওকে, সো কি হবে, সলিউবলাইজেশন হবে। তো সলিউটটা সলিউবলাইজেশন হবে। নাও দ্য কোয়েশ্চেন ইজ টুয়ার্ডস হোয়াট এক্সটেন্ট, কত দূর অবধি হবে। তখন দেখো, একটা আনডিজলভ সলিউট পার্ট আছে, একটা ডিজলভড সলিউট পার্ট আছে। তাহলে আনডিজলভ থেকে ডিজলভডের দিকে আস্তে আস্তে টেন্ড করছে ইনিশিয়ালি ডিউ টু কনসেন্ট্রেশন গ্রেডিয়েন্ট। এবং এবার দেখো, যত টাইম যাচ্ছে এক্সেস সলিডের অ্যামাউন্টটা তো ফিক্সড, আমি ইনিশিয়ালি 10 mg অ্যাড করেছি বা 20 mg অ্যাড করেছি, হোয়াট এভার অ্যাড করেছি, প্রত্যেকটা সেকেন্ডে যদি 100 মাইক্রোগ্রাম করে ডিজলভ হয়, তাহলে গ্র্যাজুয়ালি কনসেন্ট্রেশন গ্রেডিয়েন্টটা ফলো করছে। তাহলে রেট অফ সলিউট ট্রান্সফারটা গ্র্যাজুয়ালি আস্তে আস্তে কমবে, কমতে কমতে একটা পয়েন্ট আসবে, যে পয়েন্টে, যে রেটে সলিউটটা ফ্রম আনডিজলভ সলিউট টু ডিজলভ সলিউট, এই দুটো ফেজের মধ্যে ট্রান্সফার হচ্ছিল। আবার বলছি, ফ্রম আনডিজলভ সলিউট টু ডিজলভ সলিউট, এই যে রেটে এখানে ট্রান্সফারটা হচ্ছিল, সেম রেটে ডিজলভড সলিউট টু আনডিজলভ সলিউটেও ট্রান্সফারটা হবে, এই দুটো ডিকুয়ার্ড হয়ে যাবে। মানে যতটা সলিড সাবস্টেন্স থেকে সলিউশন ফেজে আসবে, ততটাই সলিড সলিউশন ফেজ থেকে সলিড সাবস্টেন্সে চলে যাবে। সো দিস ইজ বেসিক্যালি অ্যান ইকুইলিব্রিয়াম। এখানে যে বলা হয়েছে যে ইকুইলিব্রিয়াম ইজ এস্টাবলিশড, এটাই সেই ইকুইলিব্রিয়াম। ওকে, ওই পয়েন্টে, এক্স্যাক্টলি অ্যাট দ্যাট পয়েন্ট, ওই পয়েন্টে যতটা সলিউট একটা পার্টিকুলার টেম্পারেচারে ডিজলভড আছে ইন এ পার্টিকুলার ভলিউম অফ সলভেন্ট, ওটাই হচ্ছে সলিবিলিটি। ওকে, এবং ওই যে ভ্যালুটা, ওটাকে বলে স্যাচুরেশন সলিবিলিটি, এবং এই স্টেটটাকে বলে স্যাচুরেশন স্টেট। যখন একটা ইকুইলিব্রিয়াম এস্টাবলিশ হয়ে যায়, যখন ওখানে একটা ডাইনামিক ইকুইলিব্রিয়াম আছে। হোয়াই ইট ইজ ডাইনামিক? বিকজ দ্য ইকুইলিব্রিয়াম ইজ নট স্ট্যাটিক, ওখানেতে কনস্ট্যান্টলি একটা সাইকেল চলছে, ফ্রম আনডিজলভ সলিউট টু ডিজলভ সলিউট, ফ্রম ডিজলভ সলিউট টু আনডিজলভ সলিউট। ওকে, so what is quantitative approach? It is the concentration of solute in a saturated solution at a certain temperature. So basically now I expect you have understood what is the meaning of qualitative and quantitative approach of solubility, and what is that equilibrium. It's a dynamic equilibrium, why it is not a static equilibrium, right? So USP is United States Pharmacopoeia, যেটা globally different pharmaceutical companies follow করে along with some guidance document from US FDA. সো এখানে একটা চ্যাপ্টার আছে, চ্যাপ্টার 1236, and what it is telling about solubility, the concentration limit at thermodynamic equilibrium. What is thermodynamic equilibrium? যেটার কথা আমি এক্ষুনি বললাম, to which a solute may be uniformly mixed with a solvent. Okay, so any doubt from this slide? হ্যাঁ, মুস্তাক হোসেন, are you having any doubt?
No, sir.
You have understood it's a very complex concept. इतना जल्दी कैसे समझ गए?
Sir, বুঝে গেছি স্যার জিনিসটা।
ওকে, গুড। শুভদীপ দিন্দা, বুঝে গেছো তুমি?
Yes, sir.
মধু প্রসাদ, তুমি বুঝে গেছো?
सर नो सर, सर नहीं समझ आया सर।
Are you comfortable in Bengali?
सर नो सर, आई एम नॉट कंफर्टेबल इन
Okay,
बेंगोली।
then you should tell it, na? Initially, I thought everyone is comfortable in Bengali. Okay, for you. Let us assume a situation where we are having एक सिचुएशन ऐसे अंदाजा लगाओ जहां पे हमारे पास एक अनडिजर्व सॉल्यूट है, हमारे पास एक बीकर ऑफ वाटर है, वहां पे हम ऐड कर रहा है इनिशियली एंड एक्सेस अमाउंट ऑफ सॉल्यूट। इनिशियली क्या होता है, वहां पे कॉन्सेंट्रेशन ग्रेडियंट है, ठीक है। जो अनडिजर्व सॉलिड है वहां पे वो कॉन्सेंट्रेशन ज्यादा है, जो बल्क ऑफ द सॉल्यूशन है वहां पे कॉन्सेंट्रेशन नहीं है, जीरो है। तो क्या होगा, कॉन्सेंट्रेशन ग्रेडियंट अगर ज्यादा है तो वहां पे डिफ्यूजन होगा, डिफ्यूजन होके जो अनडिजर्व सॉलिड है वहां से डिजर्व सॉल्यूट में, मतलब बल्क फेज ऑफ मीडियम, वहां पे मटेरियल ट्रांसफर ज्यादा फोर्स में होगा, ज्यादा जल्दी होगा। ओके, सो द रेट ऑफ द ट्रांसफर ऑफ द मटेरियल फ्रॉम द अनडिजर्व सॉल्यूट टू द dissolved medium, dissolved solute, that is solvent, will be much higher at the initial phases, and gradually with the progress of the dynamic process, the initial excess amount of solute what we have added, that will be lesser, right? So like when at the initially we have added suppose 15 mg of solute, so after 10 minutes definitely some amount will be dissolved, and ultimately it will be 12 mg, maybe 13 mg, maybe 11 mg, whatever maybe, but it will not be 15 mg definitely. So the concentration gradient will also fall. So at different stages gradually, the more the equilibrium, more the situation will shift towards equilibrium, the rate of solubilization will be slower, and ultimately a phase will come where the rate of solute transfer from undissolved solid to dissolved solid, and the rate of material transfer from dissolved solid to undissolved solid will be same. Okay, so जो solid dissolve नहीं हुआ वहां से dissolved solid, that is solution phase, वहां पे जितना material जे रेट में आ रहा है वही सेम रेट में material solution phase से undissolved solid phase में भी जाएगा, same rate. So there will be an establishment of dynamic equilibrium, what is written here as equilibrium. Okay, and at this equilibrium the amount of solute what is dissolved in a particular volume of solvent at a particular temperature, it is known as solubility, and this stage is called saturation solubility, saturation state, where the solvent does not have the much more capability, does not have any capability, better to say, to accommodate an excess amount of solute. Okay, so Madhu, is it clear for you?
यस सर, यस सर।
Great. Let me move to the next slide. It's an important message. Don't get confused between the solubility and dissolution. Dissolution is something what is a very big part of science, and it will come in your curriculum of physical pharmacy, what I will teach you at the later phases. A lot of mathematics are there, but initially you should have some idea, basic idea about the solubility and dissolution. So what is dissolution? Dissolution is basically rate of mass transfer from undissolved solute to dissolved state. So यहाँ पे जब भी हम डिस्कस करेंगे तो ये सिचुएशन ना दोनों चीज के ऊपर डिपेंड करता है, मतलब टू थिंग्स विल स्टे इन आवर सिनेरियो, इन आवर इमेजिनेशन. ओके, वन इज योर बल्क मीडिया, one is undissolved solid, another one is dissolved solid and solvent, undissolved solid, dissolved solid. We will play with that. Okay, so the rate of mass transfer from undissolved solid to dissolved solid, this is dissolution. Okay, it's a surface dependent phenomena, it's a kinetic phenomena. Solubility is a thermodynamic phenomena. So the extent of dissolution is basically solubility. What is meaning of that? The transfer of molecules or ions from a solid state into solution is known as dissolution. The rate of transfer. Fundamentally, the process is controlled by a relative affinity between the molecules of the solid substance and those of the solvent. So the affinity in between, maybe some affinity what is driven by maybe some chemical interactions, maybe hydrogen bonding or van der Waals force of interaction, or maybe London force, that will basically define the rate जे रेटे सॉल्यूट टा सॉल्वेंट আসবে, जो रेट में सॉल्यूट सॉल्वेंट में आएगा. Okay, then that will define the affinity. The extent to which the dissolution proceeds under a given set of experimental condition is referred to as the solubility of the solute in the solvent. So this, you can see the picture here. This is the picture of HPMC. What is the full form of HPMC? Anybody? HPMC. Maybe in different times you have used some HPMC eye drops also, tear drops, just tears. This is a brand name from Sun Pharma. Okay. What is the full form of HPMC? It's a polymer. Hey, hello.
Hydroxypropyl methyl cellulose.
Great. So HPMC is a cellulosic polymer, and HPMC, when you will add HPMC in water, it will not get dissolved, but the value of solubility is very higher. So dissolution rate might be slow, the rate of mass transfer might be slow, but the extent might be higher. So this is a very good example to differentiate between these two concepts, solubility and dissolution. Okay, so for a substance, for a solid substance, its solubility in a liquid medium, maybe in water, may be much higher, okay, but the rate of mass transfer from the undissolved state to dissolved state may be lower. Okay, so dissolution rate may be lower, but solubility may be higher. HPMC is an example. Okay, HPMC डिसॉल्व करने के लिए हमें एक कॉम्प्लेक्स प्रोसीजर का जरूरत पड़ता है. HPMC का मजा क्या है? HPMC ना एट हॉट वाटर हाईली डिसॉल्वेबल, मतलब डिसोल्यूशन रेट हाई हो जाता है बट सॉल्युबिलिटी कम हो जाता है. HPMC का सॉल्युबिलिटी ज्यादा है कोल्ड वाटर में, बट डिसोल्यूशन रेट कम है. तो हम क्या करते हैं, like we are going to dissolve 10 mg of HPMC in 10 ml of water. So what we will do, we will initially take 5 ml of cold water, we will heat it, we will add 10 mg of HPMC, and as the dissolution rate is faster, it will be well dispersed, but it will not be dissolved, it will be well dispersed within a fraction of minutes. Then we will add gradually cold water in it, we will cool it, and we will keep it in the refrigerator for 4 to 5 hours. Then it will form a gel-like structure. Okay, thick viscous solution. So there are different grades of HPMC, HPMC K4M, HPMC E100 LV, HPMC E4M, HPMC E5, L6. Lots of grades are there. What the grades basically depends, what the grade basically decides. It decides if we dissolve HPMC completely in water, what will be the resultant viscosity of that media. Okay, depending upon the grades differ. So some sounds are there. So have you understood the concept? Hello.
Hello, sir.
Let me take the names. Arnab Singh, yes. Hello, Arnab. Hello. I think he has left the meeting. Arnab, hello.
Yes, sir.
So what is the difference between solubility and dissolution?
Sir, the solubility is the maximum amount of solute particles which dissolve in the solvent.
So, and what is dissolution? What is the difference?
Okay, sir.
Madhu,
Yes, sir.
what is the difference?
Sir, difference is we know the bulk transfer
See,
in
dissolution is a dynamic phenomenon. It is the rate of mass transfer from undissolved solid to dissolved solid. And solubility is the extent of dissolution. Okay, towards what extent that mass transfer process will persist. That is dissolution, that is solubility. So maybe for a system, for a solid, the extent is much higher in a particular solvent, but the rate might be slower. HPMC is an example. Is it clear? Hello, I want to hear the voice from all of you. Don't be silent. Basically, you are investing your time here, so don't waste it. If you are not getting the concepts, please let me know. Otherwise, how can I know? It's not a offline class, it's an online class. দেখো ব্যাপারটা কনসেপ্টটা যেটা হচ্ছে সেটা হচ্ছে ওকে the concept is basically what is solubility. Solubility is the extent of dissolution. So what is dissolution? Dissolution is the rate of mass transfer from dissolved solid to undissolved solid. Okay, sorry, from undissolved solid to dissolved solid. Okay, so now the question is toward what extent that mass transfer process will persist. Okay, and that extent is defined by solubility. Okay, so let me give an example. Chloramphenicol palmitate, it has a solubility of 10 microgram in water per ml of water. So maximum 10 microgram can go in water. So initially from 0 microgram to 10 microgram, at what rate it will reach, that is dissolution, and at what extent the equilibrium will persist, that is 10 microgram, and that is solubility. Is it clear now?
Yes, sir.
Great.
Yes, sir. Yes, sir.
Great. So let me move to the next slide. Yes, there are some particular definitions what you should understand. Thermodynamic solubility, the maximum amount of the most stable crystalline form of the compound. So what is mostly stable crystalline form of the compound? There is a concept called polymorphism. So a particular solid, it might have a same chemistry, but it might have different crystalline structures. Okay, depending on the order or arrangement of crystals in the lattice. Okay, it may form different crystalline structures. So this different crystalline structures, what are chemically equal, are called polymorphs. There might be different polymorphs, but these polymorphs usually differ with respect to their free energy, Gibbs free energy. What I think you have studied already in your physical chemistry classes, Gibbs free energy. So this Gibbs free energy, depending upon the Gibbs free energy, the stability of these polymorphic forms may also differ. So when we will talk about thermodynamic solubility, we will talk about the mostly stable crystalline form. So what is having the lowest Gibbs free energy, okay, and the highest entropy definitely of the compound that can remain in solution, okay, at a given volume of the solvent at a given temperature and pressure under equilibrium condition. So there are some conditions at a given volume of solvent at a given temperature and pressure and under equilibrium condition. Okay, so these are the variables of thermodynamic solubility. Thermodynamic solubility is nothing but a function of this. It is a function of solute, it is a function of nature of solvent, it is a function of volume of solvent, it is a function of temperature, it's a function of pressure. If we vary these parameters, we can vary the thermodynamic solubility of a solute in a solvent. Okay, intrinsic solubility, that is aqueous solubility of pure uncharged compound. So sometimes some molecules basically show pH dependent solubility, and at ionized state they show much more solubility in comparison to the unionized state. So intrinsic solubility strictly confine the definition of solubility to a point where we will only talk about the uncharged compound or unionized compound. Is it clear? And the third one concept is kinetic solubility. The solubility at a time when an induced precipitate first appears in the solution. So what is the meaning of that? Kinetic solubility does not consider the impact of lattice structures. Okay, what thermodynamic solubility considers. What is lattice structure? I think I have already taught you about lattice structure in the last class of solid state under states of matter. So what happens? We basically dissolve our drug in a particular organic solvent, maybe DMS, and we gradually add it in an aqueous solvent under stirring condition at a fixed temperature, and at a point when some evidence of precipitation occurs. So when precipitation will happen, when it is a point when we will cross that saturation condition. So we will measure that point and we will report it as kinetic solubility. It is nothing but a time dependent phenomena, kinetic phenomena. Kinetic means time dependent. So with time it will change. Okay, so this is all about thermodynamic solubility, intrinsic solubility, and kinetic solubility. Any doubts?
স্যার ইন্ট্রিনসিক সলিবিলিটিটা যদি একবার বলতেন।
Yes, aqueous solubility of pure uncharged compound. Here, one term is very important: pure uncharged. There are some compounds, maybe weakly acidic or weakly basic. This weakly acidic or weakly basic compounds, when it comes in water, depending on pH of the water, it may stay in an unionized form or in an ionized form. So the ionized form solubility will be much more higher in comparison to the unionized form. So intrinsic solubility is something where we are measuring the solubility of unionized compound, okay, in water or any other solvent, right? So unionized compound, not ionized, right?
Yes, sir.
Kinetic solubility.
Yes, kinetic solubility is time dependent solubility. In case of thermodynamic solubility, basically I have also something to say about all these things. Kinetic solubility is a time dependent solubility. What we do here, we take the solute, we dissolve it in an organic solvent, but it is highly soluble, maybe DMSO, maybe methanol or some other organic solvents. Then we gradually add it in water under starting condition at a particular temperature. And when we are gradually adding it, so at a particular, after a particular fraction, it will cross its saturation condition and precipitation will happen, right? Because it will go beyond that equilibrium. So precipitation is definitely going to happen. So when precipitation will take place, so what will happen? So some turbidity will appear, and we measure the solubility at that particular point. It is called kinetic solubility. Is it clear? So kinetic solubility does not consider the impact of lattice effect. What is the basic difference between thermodynamic solubility and kinetic solubility? To measure thermodynamic solubility, a lot of time is required because here we are adding the mostly stable crystalline form. So here dissolution rate matters. Okay, because we are adding the solute in the solvent in solid form. So the rate at which it will dissolve, it will define after which time period the equilibrium will attain, right? But in case of kinetic solubility measurement, we are adding it in a liquid form, in a dissolved form. So here we are neglecting, we are destroying the effect of crystal lattice structure initially. So almost after 1 minute or 2 minutes, you will get that value. It's an instantaneous thing. Okay. So basically, HTS can be applied, high throughput screening can be applied for kinetic solubility measurement. And there is a standard method for measurement of thermodynamic solubility. A lot of methods are there, potentiometric method, blah, blah, blah. These are not used nowadays. The most popular method is sec plus method. You can note down that. So what we do here, we take a particular volume of solvent, we add our solute in an excess amount here, and basically we keep it in Sekar bath. What is Sekar bath? Here, the vial is maintained at a constant temperature by addition of water. You can also see in your institution what is Sekar bath apparatus, and it gives a constant shaking to the solute. Okay, so this helps to attain the equilibrium. Okay, so we get a measure of the solubility at 24 hours, 48 hours, and 72 hours. So when the maximum extent will reach, the concentration dependent solubility plot, okay, that time dependent solubility plot, it will reach a plateau value. Okay, like the solubility of 48 hours will be same as that of the solubility of 72 hours. So this is the value of thermodynamic solubility. Wait until some equilibrium or plateau happens. So is there any doubt? Samuel Kumar, what is your full name? Hello. Samuel.
Yes, sir.
Is that concept clear?
Yes, sir.
Great. Sujoy.
Yes, sir.
Have you understood?
Yes, sir.
Madhu Prasad, you were asking about kinetic solubility. Is it clear?
Yes, sir. Sir, I want to tell you something, sir.
Yeah, definitely.
Sir, please be little slow. Sir, I am not able to follow you, sir.
Okay. I can be little slow, but the issue is, the syllabus is very big, so I have to cover a entire thing in a very short period of time. I am trying my best, but you have to be also very much attentive. Okay, otherwise, the syllabus of pharmaceutics is very huge, so we have to cover everything. So yes, at a particular point when you will feel that you are not getting the things, just raise your hand and tell me. I will reduce my speed and I will again discuss the thing. Okay,
Okay, sir.
great. So is the concept clear to you, kinetic solubility?
Yes, sir.
Great. Uh, Let us take a 5 minutes break. Then we will move to concept of saturation. Hello, hello, hello. Are you here?
Yes, sir.
Yes, sir. Yes, sir.
Okay, okay. So let us begin again. Concept of saturation. So what is saturation? Just sometimes ago, I have told you the concept of saturation. This is a pictorial representation of that concept. This is a test tube. When we are initially adding solute, the capacity of the solvent to accommodate solid is still higher. At that phase, it is called undersaturated solution or unsaturated solution. Okay, so here more amount of solute will dissolve. So we are gradually increasing the concentration of solute, and at a point there will be an equilibrium, there will be a dynamic equilibrium, what I have told you, and at that phase the solution will reach to saturation, and it will called as saturation solution, saturated solution, and the value of solubility will be known as saturated solubility. Okay, saturation solubility or saturated solubility. And if the initial solid form is mostly stable crystalline form, then it will be called as thermodynamic solubility. And still beyond the saturation point, if we increase the concentration, then there are some spaces where the solvent can accommodate a little amount of solute more than that of the saturation solubility. It is called supersaturation state. It's a highly unstable state and a minimal disturbance, like if we add a single piece of crystal, or if we fluctuate, if we take the flask, if we move it, or if we increase the temperature or cool it, so if we bring some temperature fluctuation, immediately precipitation will occur. Okay, so there are three phases. So one is unsaturated solution, another one is saturated solution, another one is supersaturated solution. So supersaturated drug delivery system, it's a very huge domain of current research. A lot of modified solid forms like amorphous solid dispersions, co-crystals, what I will teach you in advanced pharmaceutics module, are basically based on the principles of supersaturated solution. Okay, and this is a pictorial representation of temperature concentration plot. Here you can see we can play with this undersaturation, saturation, and supersaturation by varying the playing parameters. Like at this point, you can follow my cursor. This is supersaturated solution. This is a solubility curve. Okay, so this represents the thermodynamic solubility at different temperature. So you can see here at this temperature, the thermodynamic solubility value will be like this, and at this point it will be supersaturated, the solution will be supersaturated. So if we increase the temperature, the solubility value will increase because of the movement of the solvent molecules. There will be much more vacant places among the solvent molecule to accommodate the solute, and this is the reason why with the increase in temperature, the thermodynamic solubility or saturation solubility value will be increased, and this is the consequence. With the same concentration, if we do nothing, if we just increase the temperature, you can see from supersaturated, the system will shift to saturation condition. And if we increase the temperature further, we can see here from saturation condition, the system will shift to unsaturated condition. So at this temperature, we can see here the saturation concentration will be in this point, and beyond this point, supersaturation will occur. So any doubt? Any doubt? Yes, hello.
No, sir.
It is clear the concept of undersaturation, saturation, and supersaturation.
No, sir.
Yes,
No,
sir.
Sir, supersaturation is not clear, sir.
देखो सैचुरेशन कंडीशन जहां पे एक इक्विलिब्रियम एस्टेब्लिश कर रहा है, उसका ऊपर भी ना जो सॉल्यूट होता है वो अगर आप ऐड किया टेम्परेचर फिक्स करके, तो सॉल्वेंट का कैपेबिलिटी होता है थोड़ा बहुत वो एकोमोडेट कर लेते हैं. इट इज काइनेटिकली स्टेबल बट थर्मोडायनामिकली अनस्टेबल. सो उस पॉइंट में अगर आप थोड़ा सा फ्लक्स लेके एजाइटेशन करो और एक दो क्रिस्टल ऐड कर दो और टेम्परेचर थोड़ा ज्यादा फ्लक्चुएट करो, तो वो जो मेटास्टेबल इक्विलिब्रियम वहां पे था वो ब्रेक हो जाएगा, एंड इट विल रीच टू stable equilibrium, that is saturation, by precipitating the excess amount of solute what the solvent priorly accommodated to reach the supersaturation. Okay, this is called supersaturation state. And हम अगर ये टेम्परेचर को लेके ज्यादा काम करेंगे तो at the same concentration the solution phase may be changed from undersaturation to saturation to supersaturation, because if you increase the temperature there will be an increase in the thermodynamic solubility of the solute as well. क्यों ये होता है? क्योंकि एक सॉल्वेंट कितना सॉल्यूट एकोमोडेट कर पाएगा ये डिपेंड करता है जो सॉल्यूट मॉलिक्यूल से दो सॉलिड मॉलिक्यूल, उसका बीच में कितना स्पेस है उसके ऊपर, अगर आप टेम्परेचर बढ़ा दो तो उसका बीच में जो वाइब्रेशन और मोशन है ना वो ज्यादा हो जाता है, तो बीच का जो डिस्टेंस है और बीच का जो वैकेंट स्पेस है वो भी ज्यादा हो जाता है। इन द लैंग्वेज ऑफ फार्मास्यूटिक्स हम उसको कहते हैं कैविटी, तो कैविटी वॉल्यूम ज्यादा हो जाता है, तो वहां पे टेम्परेचर बढ़ाने के साथ साथ वो मोर और ज्यादा वो सॉल्यूट एकोमोडेट कर पाता है। तो दिस इज द रीजन why if we increase the temperature or reduce the temperature, we can play with the solubility, that is saturation solubility, and we can change the system maybe from undersaturated to supersaturated or supersaturated to saturated or to undersaturated. Is it clear now? Hello Madhu, is it
Yes,
clear?
sir. Yes.
Okay,
Yes.
great. So yes, this is something what I would like to share. If you are having any doubt, please raise your hand and ask. Mechanism of solvation. See, follow this pictorial representation. This is a crystal and this is the boundary layer. So what happens when basically a crystal gets dissolved or a solid material get dissolved, a solvent rich layer where the concentration of solute in that layer will be much higher in comparison to the bulk. Okay, it basically becomes very much attached to the solid surface. This is called boundary layer. And if we see here, the maximum amount of solid is present just at the surface, and gradually if we move through the boundary layer, it is gradually reducing up to that point, and this is the bulk of the medium. Here a same concentration is present. Okay, so there is a variation, there is a distance dependent variation at the boundary layer, initiating from the surface of the initial solid to the boundary between the bulk solvent and the boundary layer. Okay, at the bulk solvent the concentration is constant, and this is the mechanism of solvation what I have just told you. This is your crystal lattice structure. These are solvent molecules, this is coming out, and when it is getting dissolved, before that you need to create some space, what is called cavity. So a particular lattice is broken and the solid crystal is coming out, and a cavity is being created in the media, in the solvent, and your solid is getting accommodated in between that cavity. Okay, so this is a better pictorial representation. Here you can see this is a solvent molecule and these are solid molecules. The solute is getting dissolved, it is coming in the solvent, and here is a cavity is present and it is just getting accommodated in the cavity. So for solvation, a particular equilibrium is very important. For example, if your solvent molecules are A and your solute molecules are B, there are three kind of acting forces in the whole scenario. One is AA, one is BB, one is AB. So AA and BB, these forces are known as cohesive force of interaction, and AB, that is the attraction force in between the solvent and solute molecule, is known as adhesive force of interaction. So for a particular solute to get dissolved in a solvent at a particular temperature, the adhesive force of interaction in between the solute and the solvent molecule must be higher than that of the cohesive force of interaction in between the solid molecules and the solvent molecules. Okay, so what if the adhesive force of interaction does not become higher in comparison to the cohesive force of interaction? So if the adhesive force of interaction in between the solute and solvent molecule become lower than that of the cohesive force of interaction in between the solid molecules, the crystal structure will not be broken. Okay, and if the adhesive force of interaction in between the solid and the solvent molecule does not become higher in comparison to the BB attraction force, that is the cohesive force of interaction between the solvent molecules, the cavity in the solvent will not be created. So basically solvation is a combined harmony of three processes. One is breakage of crystal lattice, one is formation of cavity and accommodation of cavity, and depending on that, three energies are important. One is lattice energy, one is cavitation energy, one is solvation energy. Okay, so this is all about mechanism of solvation. Any doubt? Is it clear to all of you? Hello.
হ্যালো স্যার, এ বি বলতে আপনি কোহেসিভ অ্যাডিসিভ যেটা বললেন ওটা
Yes,
যদি
yes.
স্যার বলেন।
দেখো এখানেতে see here three force of interactions are persisting. One is the adhesive, one is the attractive interaction in between the solute molecules. Solute molecules, okay, that is solids. If we consider the solid molecules as A and if we consider the solvent molecules as B, then AA, this is an attractive force of interaction in between the like molecules, that is solute, and it is known as cohesive force of interaction. Similarly, BB in between the solvent molecules, the attractive force of interaction is known as also cohesive force of interaction, but it is among the solvent molecules. So what is cohesive? Cohesive means the attractive force of interaction in between the like molecules, and between the unlike molecules is known as adhesive force of interaction. So the attractive force of interaction in between the solid and solvent molecule, that is AB. Okay, it is called adhesive force of interaction. And for solubilization, the adhesive force of interaction in between the solid and the solvents must be higher in comparison to the cohesive force of interaction in between the solids and the solvents. Okay, like solid molecules, that is AA and BB. So AB must be higher in comparison to AA and BB. Is it clear?
Yes, sir. Yes, sir.
Great. Expressions of solubility. I will come here at later because you have to solve some mathematics. I will give you 5 minutes of break and I will tell you to solve this. Solute solvent interactions. So basically, we are just talking about AA, BB, AB. So if we talk about AB, that is the adhesive force of interaction between the solute and solvent. So what kind of force, what kind of attractive force will persist in between the molecules of solute and solvent? It will depend on the nature of the solvent. It might be polar, it might be non-polar, it might be semi-polar. Okay, there are different categories of solvent. Polar solvents are basically protic solvents. Here the main driving force behind the solubilization is dipole moment. So what is dipole moment? Let me understand the concept. If we assume HCl, okay, hydrogen chloride, here electron cloud will be shifted towards chlorine atom because of its higher electronegativity in comparison to hydrogen, and a local distribution, local non-equal distribution of electron cloud will be there. The much more electron cloud will be towards chloride atom and less electron cloud will be there towards hydrogen atom. So chloride atom will take a temporary negative charge and hydrogen atom will take a temporary positive charge, that is charge formation. And dipole moment is basically the product of the charge and the distance of separation. This is an example of barium difluoride. Here barium is the center. You can see here fluoride are much more electronegative in comparison to barium and beryllium, and it is basically attracting the electron clouds towards it, and it is basically becoming electron vacant. So it is basically taking a positive charge, and this is taking a negative charge, and it's a multiple. It's a product of charge with the distance of separation. This is the distance of separation. Okay, so this is dipole moment. Dipole moment is the reason why the solid molecules are getting dissolved in the polar solvents, because polar solvents are basically have some polarity. So polarity, from where this polarity is coming? The polarity matlab charge. The charge is coming from dipole, because you can see here is negative charge, here is positive charge, and this charge is basically what it is doing here. It is basically imparting some charges to the solute molecules itself, and ultimately uh, there will be an ionic force of interaction what will be predominating, and ultimately the solute will be dissolved in the solvent. There are lots of examples. Along with dipole moment, hydrogen bonding is also another thing what is important, what is predominant in case of polar solvents. And another important thing is ratio of the polar to the non-polar groups of the molecule. So basically each molecule, each solid molecule have two portions. So one is polar portion, another one is non-polar portion. For example, if we talk about methyl chloride, here methyl, that is alkyl part, this alkyl chain is the non-polar portion and chloride is the polar portion. The more we will increase the alkyl group from methyl, if we shift to octyl or butyl, then the ratio of the polar to the non-polar group will be reduced. Okay, there are some examples: alcohol, aldehyde, ketones, and amines. These are basically polar solvents. So we will shift to the non-polar solvents. So ionic and polar solutes are not soluble. One concept you should keep in your mind always for solubilization: like dissolves like. So polar solutes will be dissolved in the polar solvent, non-polar solutes will be dissolved in the non-polar solvent. Ionic and polar solutes are not soluble or are only slightly soluble in non-polar solvent. So what are the main driving force behind the solubilization of uh, non-polar solutes to the non-polar solvent, or in a different angle? The question can become like that: why polar solute does not get dissolved in the non-polar solvent. You can see the two words, what is written in the red color. These are the reasons why polar solutes does not get dissolved in the non-polar solvent. These are low dielectric constant and inability to form hydrogen bond. So why they are unable to form hydrogen bond? The reason is to form hydrogen bond you need an electronegative atom, and non-polar solvent does not usually have an electronegative atom, what basically will attract the electron cloud towards it. This is the reason why they can't form hydrogen bond. So however, non-polar solvents can dissolve non-polar solutes with similar internal pressure through induced dipole interaction. So what is induced dipole interaction? You can see here, this is a particular solvent. Maybe it's a water molecule. Okay. So this water is a polar solvent, and this hydrogen is carrying a partially positive charge and this oxygen is carrying a partially negative charge, and this is an oxygen molecule. What is a non-polar apparently, but in presence of this negatively charged oxygens of water molecule, some electron clouds from this oxygen will go towards this and it will be partially positively charged, and similarly when it is becoming positive charge, it will attract some, this oxygen will attract some electron towards it and it will be in partial negative charge. So this is the reason why some induced dipole interaction takes place, and this is the reason behind the solubilization of non-polar solutes to the non-polar solvent. Okay, and also there are some involvement of weak van der Waals force of interaction or London type force of interaction behind the solubilization of non-polar solutes in the non-polar solvents. So let us come to the semi-polar solvents. So these are the transition state between the polar solvents and the non-polar solvents. Semi-polar solvents such as ketones or alcohols can induce a certain degree of polarity in non-polar solvent molecules. Okay, by induced dipole interaction. So here we have to add some polar solutes to the non-polar solutes. Okay, to the non-polar molecules, and the combination is called semi-polar. And semi-polar compounds can act as an intermediate solvents to bring about miscibility of polar and non-polar liquids. Right. For example, you are having a particular solute what is soluble in alcohol, but you want to solubilize it in water. So what you will do, you will add a little bit of alcohol in the water, and with the help of alcohol present in the water, you can dissolve a much more amount of that solute in that resultant semipolar solvent in comparison to the capacity of the non-polar solvent, that is water, to dissolve that particular solute. This approach is called co-solvent approach. There are a lot of pharmaceutically approved co-solvents like ethanol, like polyethylene glycols, but most of these co-solvents are toxic. So there are very little products currently in market, and you can see here, this is a chart of dielectric constant along with the polarity of different solvents. You have to memorize it because some questions comes from this chart in GPAT. Any doubt in the sector solute solvent interaction?
হ্যালো স্যার,
Yes, yes.
তো কোসলভেন্ট অ্যাপ্রোচটা যে কি?
হ্যাঁ, কোসলভেন্ট অ্যাপ্রোচটা এটা যে তুমি ধরো একটা কোনো পার্টিকুলার সলিউট যেটা ওয়াটারে ডিজলভ হয় না, ওটাতে BCS2 আর 4 মলিকিউল তুমি জলে ডিজলভ করতে চাইছো, জলে ওটা ডিজলভ হয় না, ওটা অ্যালকোহলে ডিজলভ হয়। তুমি তাহলে অ্যালকোহল ওখানে জলে একটু অ্যাড করে দাও, তাহলে কি হবে, তোমার জলে যতটা সলিউট অ্যাড হতে পারছে তার থেকে অনেক বেশি সলিউট তোমার ওই হাইড্রো অ্যালকোহলিক মিক্সচারটা অ্যাড হবে। কেন? কারণ হচ্ছে এখানে ওয়াটারটা ছিল একটা পোলার সলভেন্ট, অ্যালকোহলটাও পোলার সলভেন্ট, বাট দুজনের মধ্যে পোলারিটি ডিফারেন্স আছে। এখন যখন তুমি ওখানে অ্যালকোহল অ্যাড করছো, রেজাল্টেন্ট সলভেন্টটা হচ্ছে সেমিপোলার। ওই সেমিপোলার যে সলভেন্টটা, ওই সেমিপোলার সলভেন্টটার মধ্যে ইনডিউস ডাইপোল ইন্টারাকশন হয়। ওই ইনডিউস ডাইপোল ইন্টারাকশনের জন্য ওভারঅল পোলারিটি চেঞ্জ হয়ে যায় এবং ওটা ওই সিমিলার পোলারিটি কোনো সলিউটকে ডিজলভ করে দিতে পারে। বুঝতে পারলে? ইটস অ্যান টেকনিক টু ইনক্রিজ সলিবলাইজেশন। কোনো ডাউট শুভদীপ?
নো স্যার।
Great. Anyone who is having some doubt in understanding the concepts? Okay. I will share this table with you. Factors affecting solubility: temperature. What is the temperature dependence of solubility? That I already told you. Pressure usually we keep constant. This is not a very important factor. chemical nature of solute and solvent. If we change the solute, if we change the solvent, we can also change the solubility. So just see this chart. Is there anything abnormal? See, potassium nitrate, if we increase the temperature, we are observing an enhancement in solubility. NaCl, similar scenario is there. We can see here sodium sulfate decahydrate. After a particular temperature, it is forming anhydrous sodium sulfate, and that anhydrous sodium sulfate, if we increase the temperature, we are watching an reduction in solubility. So this is a reverse trend. This is an exception. Any one of you having any idea why this kind of phenomena is happening, where we are increasing the temperature and we are observing a reduction in solubility? Madhu Prasad. Yes. Do you have any idea why this kind of phenomena is taking place? Just try. I don't expect the right answers from you, but definitely you should develop some thought power in yourself. Your thought process should be correct. Hello. Madhu Prasad, hello.
Yes, sir.
Yes, tell me about your understanding about that phenomena. We are increasing the temperature, but solubility is getting reduced. It's a exceptional phenomena. So just tell me the reason for sodium sulfate decahydrate to sodium sulfate anhydrous. Hello. Yes, at least tell something. Hello.
Sir, due to the concentration.
No. Mustaq Hussain. Yes.
মানে সোডিয়াম যেটা হাইড্রেটেড ছিল ওটা কিন্তু টেম্পারেচার বৃদ্ধির সঙ্গে সঙ্গে ওটা ডিহাইড্রেট হয়ে যাচ্ছে, যে কারণে সলিবিলিটি কমে যাচ্ছে।
No, 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 no. Piyojit Khan.
Sir, due to exothermic.
Exotherm. Yes, this is something what is very important phenomena. But yes, you also can you clarify? Can you elaborate?
Because when the temperature increase, when concentration increase, the temperature will also increase, and this process is related to exothermic.
Exothermic what? Piyojit Khan.
No, sir.
Saurabh Vadai. That Saurabh Mundal. Subhadip Dinda is thinking, मैं बच गया. No, Subhadip Dinda. Yes, you tell.
Yes, sir.
Any idea?
No, sir.
Hey, at the beginning of the class, there were total 10 students, but now there are only 1 to 6 students. Why? Are you not getting the topic? Maybe. So let me understand the phenomena. Dissolution is the only phenomena in world what is a spontaneous process, but still it is exothermic. Okay. So dissolution is spontaneous only when it is exothermic, and it is specific for some phenomena, for some solutes. Dissolution may be endothermic also sometimes. Okay, and when dissolution will be an exothermic phenomena and when dissolution will be an endothermic phenomena, that will depend entirely on the nature of the solute. Initially, the solute is present in sodium sulfate decahydrate form. It's an hydrate form. So basically, when we are increasing temperature, the water molecules are getting evaporated, and it is basically losing its water molecules. And at that phase, the dependence of dissolution was on endothermic phenomena. It was an endothermic phenomenon. So it was thermodynamically favorable. We are increasing temperature. We are supplying heat. So at 32.5 degrees Celsius temperature, that is at this point, it is losing all its water molecule, and it becomes converted to anhydrous form, anhydrous sodium sulfate. So at this point, there is a dramatic change. The dissolution becomes dependent on exothermic phenomena. Up to that point, dissolution was endothermic phenomena, but beyond that point, dissolution was exothermic phenomena. So here we are applying temperature. So we are doing an opposite phenomena in comparison to that what was thermodynamically favorable. because here dissolution was an exothermic phenomena. So it will evolve heat, it will generate heat, but we are supplying temperature here. So basically we are violating La Chatelier's principle here, and this is the reason why the solubility is getting reduced with increasing temperature. Is it clear to everyone?
স্যার
Very
এখানে আছে
yes, yes.
স্যার এখানে 25°C তো স্যার ওয়াটার ভেপারাইজেশন হয়
25 কি?
বাষ্প হয় না ডিগ্রি সেলসিয়াসে, তো জল বাষ্প হয় না, তো কিভাবে হচ্ছে এটা?
জল বাষ্প হওয়া তো দরকার নেই। আমরা যখন এখানে হিট করছি তখন এখানে ওয়াটার মলিকিউল গুলো যখন হাইড্রেট ফর্মে ছিল, ভেরি গুড কোয়েশ্চেন, তখন ওটা ল্যাটিস স্ট্রাকচারের মধ্যে ছিল। যখন তুমি টেম্পারেচার বাড়াচ্ছ কাইনেটিক মুভমেন্টটা বেড়ে যায় ওগুলোর, ফলে ল্যাটিস স্ট্রাকচার থেকে ওটা বেরিয়ে আসছে, বেরিয়ে এসে ওটা বাল্ক ওয়াটারের মধ্যে মিশে যাচ্ছে। বুঝতে পারছো?
স্যার ওটা কত ডিগ্রি টেম্পারেচার হচ্ছে?
এটা 32.5। এখানে কোনো ইভাপোরেশনের গল্প নেই, মলিকিউলটা ল্যাটিস স্ট্রাকচারের মধ্যে ছিল, ওই টেম্পারেচারে পরে ওই মলিকিউলটার কাইনেটিক মুভমেন্টটা বেশি জোরে হচ্ছে, ফলে ওটা ল্যাটিস স্ট্রাকচারের মধ্যে থাকতে পারছে না, কারণ ওয়াটার ইজ ওভারঅল সলভেন্ট মলিকিউল। ওটা বাইরে বেরিয়ে আসছে, বাইরে বেরিয়ে এসে বাল্ক ওয়াটারের সঙ্গে মিশে যাচ্ছে। বুঝতে পারলে? ওকে, সো you will again take a break of, I will give that mathematics as your homework. We will not take further break. We will cover the entire syllabus of these modules, and then we will. Okay. So thank you. Any doubts from this module? Then we will go to solubility 2. I know topics, what I am telling is basically some advanced topics, but when you are aiming for getting admitted in hyper, then definitely you have to be advanced. তোমরা তোমাদের ফিজিক্যাল ফার্মাসি ক্লাস হয়েছে কলেজে? চলছে? এগুলো পড়োনি তো? কনসেপ্টগুলো ক্লিয়ার নেই কেন? ओके 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 ओके, 1 मिनट। एसी ऑफ ही था, मैं आके ऑन किया।
हाँ मैं वो इसीलिए ऑफ किया था इसके लिए।
तो आपका काम था?
हाँ माइक्रोस्कोप
ऑफ करते हैं
तो कितना देर लगेगा?
40 मिनट्स मैक्सिमम ऑन।
ठीक है मैं लगा तो देखता हूँ, कर लेता हूँ। अगर प्रॉब्लम आता है तो
कल भी हम किया यूज, वो क्या नाम था, हाइस्प्रेटिन का मेल्टिंग पॉइंट चेक किया, ठीक ही आया।
ठीक है
7-8 का डिफरेंस आ रहा है, 7-8 डिग्री का, 3 बजा का।
ठीक है अभी
कल एक बार कॉफलर पॉइंट ट्राई किया उसके लिए, लेकिन
हाँ मैंने उसको बोला था कर ले एक बार वो
कूलिंग करके क्रिस्टलाइज नहीं हो रहा है हाइस्प्रेटिन, एमोर्फस बन चुका है।
क्लास 3 होगा। कांटेक्ट में नहीं रखा
ना ना, पहले तो कंपोनेंट ए को हीट करना पड़ता है, फिर कोल्ड करके उसको क्रिस्टलाइज करना पड़ता है, फिर दूसरा कंपोनेंट को डालना पड़ता है और उसको मेल्ट करना पड़ता है, और मेल्ट करने के बाद उस मेल्ट में कंपोनेंट 1 डिसॉल्व हो रहा है या नहीं वो देखना पड़ता है।
हाँ अगर ऐसे इश्यू आता है रेस्पिरेटरी में, अगर क्लास 3 में आता है क्रिस्टलाइजेशन तो क्रिस्टलाइज नहीं होगा,
नहीं होगा ना, वही ना।
हाँ तब वो ये क्या करना पड़ेगा, दोनों मटेरियल्स को
एक
साथ रखना है। जब रेस्पिरेटरी मेल्ट होगा, रेस्पिरेटरी हाइड्रोजन और ये क्या बोलते हैं इसको,
हाइस्प्रेटिन हायर मेल्टिंग, तो लोअर मेल्टिंग मेल्ट होगा पहले।
रेस्पिरेटरी का मेल्टिंग कितना है?
हाइस्प्रेटिन का मेल्टिंग 227 के आसपास है।
इसका इन द
120
120 नहीं है 200 है।
200 की।
हाँ तब अगर ऐसे प्रॉब्लम आ रहे तो एक और ऑप्शन है, दोनों को मिला के।
लेकिन आपका फिल्म नहीं होगा, हमको तो फिल्म बनाना पड़ेगा वो देखने के लिए।
नहीं सॉल्वेंट्स में दोनों को इक्वल डिसॉल्व करके डाल के पार्शियल ऑपरेशन कर लेना, दोनों का पहले ये दोनों का बायरेफरेंस देख लेना इंडिविजुअल, फिर ये कंबाइंड सॉल्वेंट मिक्सचर का बायरेफरेंस और मेल्टिंग देख लेना। मॉडिफाइड कोफ्लर करने के लिए बोला था उसको, मॉडिफाइड कोफ्लर मतलब हम वो मत फॉलो करना, ठीक है हमारे इसमें तो नहीं था, समझ रहे हो? ये भी कर सकते हैं, समझ गए ना तुम्हें क्या बोल रहा हूँ? पहले सॉलिड डिसॉल्व करो, मैं इसलिए कैविटी स्लाइड मंगाने के लिए उसको बोला, कैविटी स्लाइड में कैविटी फिल कर दो और उसको स्लो सॉल्वेंट इवेपोरेशन करो, ऐसे तो मन 30 या 40 मिनट्स में रख के, ओपन ही रख के इसको ऑफ करके सॉल्युबलाइज हुआ, फिर एक कुछ भी रेसिड्यू तो फॉर्म होगा, ठीक है, उसको बायोरेफ्रिजरेशन मोड पे पहले ऑब्जर्व करो,
समझ गया। फिर उसमें दूसरा सॉल्यूट डाल के उसको मेल्ट करना पड़ेगा, दोनों मिक्स हो रहा है।
नहीं तो हाँ बायोरेफ्रिजरेशन मोड पे उसको ऑब्जर्व करो, अगर उसकी क्रिस्टलाइन नेचर पहले दो कंपोनेंट की क्रिस्टलाइन नेचर से अलग आ रहा है तो कुछ फॉर्म हुआ है, तो उसको फिर से 30 जाके फिर से मेल्ट करो, तो अगर मॉडिफाइड मेल्टिंग आया फिर वो रेशियो को लेके डीएससी में टेस्ट करो।
उसका सैंपल मंडे से डीएससी का भी भेजते हैं ना सीएल में, वो भी स्क्रीन हो जाएगा एक साथ।
हो जाएगा, मतलब मैं बोल रहा हूँ एक क्लास चल रहा था ना, हम डिस्कस करेंगे तो दिन
कोई बात नहीं, मेरा और 10-12 स्लाइड ही बाकी है,
तो मैं यही था प्लीज ऑफ करूँ, मुझे तो उधर बैठ जाता 200 में चुड़ैल तो अभी यहाँ नहीं है ना।
हाँ मैं वहाँ पे वो अरुणा देवी, कोई बात नहीं, मैं अभी अभी करना है आपको तो कैसे आप कर सकते, कोई बात नहीं। Hello. So let us begin to the second module. So beyond that point, we have to know about the concept of solubility of liquid in liquid. Up to that point, we were talking about the concept of solubility of solid in liquid. But after that point, we are hello. Am I audible? Great. So now we will teach. We will know about the concept of liquid in liquid. Okay. So prior to that point, we have to remember that the concept of solubility of a liquid in a particular liquid, it is not called solubility, it is called miscibility. So this is the basic difference between the solubility and miscibility. Solubility is basically solubility of solute in a liquid solvent, and solubility of a liquid in a liquid solvent is called miscibility. Okay. So that miscibility can be complete, maybe partial also. So what is complete miscibility? When the polarity difference between the components is low. So if liquid A and liquid B, these two liquids are completely miscible, they will be completely miscible in all proportions at all temperatures. Okay. But some interesting stories come for partially miscible liquids. Okay. So when this particular situation arises, when the polarity difference between two components is very high. Okay. So in that case, it basically forms a semipolar liquid. In the previous module, I have taught you about semipolar solvents. So semipolar solvent, how we can prepare a semipolar solvent, we have to add a particular solvent with a particular dipole moment, or what may be very high, to a particular solvent having a very low dipole moment, and ultimately we will get a resulting intermediate dipole moment, what is called semipolar solvent. And a characteristic feature of that semipolar solvent is the polarity difference between the component is high. Okay, so for completely miscible liquid composition or combination, they are miscible in all the proportions, but a temperature dependence will come for partially miscible liquid combination. So what happens? The mutual solubility of two components in a partial miscible liquid combination will depend on the temperature in a directly proportional manner until a particular temperature, and that particular temperature is called critical solution temperature. Okay, CST. Or also it is known as consolute temperature. So beyond this point, the system becomes a single phase system. Okay, below this point, two phases will exist and a miscible phase will exist also. So what is the concept? Liquid A is becoming dissolved in liquid B, liquid B is becoming dissolved in liquid A at a particular temperature what is below than that of the critical solution temperature to a particular extent. So up to that extent it will be soluble. So there will be a mixed zone, and apart from that miscible zone, there will be two other segments what are separated, phase separated liquids. And when we will go beyond that critical solution temperature, so we will see they will behave like completely miscible liquid. So beyond that temperature, they will be miscible in all the temperatures, in all the proportions. Sorry. So that will form a single phase transparent liquid. Below that temperature, they will form phase separated turbid liquid. Okay. So this is the concept of critical solution temperature. So and also it is known as upper consolute temperature. Is it clear? You are having any doubt? Madhu Prasad.
Yes, sir.
हाँ, कोई डाउट है?
No, sir.
Great. Piyojit Khan.
Sir, no, sir.
Great. So now the question is, just go through the definition. For a pair of partially miscible components, the temperature above which the components are miscible in all the proportions, it is called upper consolute temperature. For an example, phenol water system, it is something what shows critical solution temperature, what is basically higher critical solution temperature or upper consolute temperature. So now the question is, can we find a reverse trend? Can we find a lower consolute temperature when the same phenomena will happen if we reduce the temperature? Okay, in the previous scenario, we were increasing the temperature and we were getting a particular temperature beyond which two immiscible liquids were completely miscible at all the proportions. So basically they were forming a completely miscible liquid. So in that case, we will cool the temperature, and beyond a particular temperature, at all proportions, these two liquids will be completely miscible. Okay, so can we find such a trend? That is called lower consolute temperature. Any idea about that? Yes, this kind of phenomena also happens for acetone water mixture. Okay, and can both of these extremities coexist? Like, is there any system where lower consolute temperature and upper consolute temperature, both of these temperatures will coexist? An example of such a kind of system is nicotine water. And is there any system where both of these extremities does not exist? Yes, an example is ethyl ether water system. Okay, so let us move to the next concept, the influence of solvent on solubility of drug. So the solvent can influence the solubility of drug by two processes. One is the impact of solvent pH on ionization behavior of drug, another one is co-solvency. Already I have taught you about co-solvency, so let us discuss about the impact of solvent pH on ionization behavior of drug. Okay, so you can see the plot here. Let me enlarge the slide. Here in x-axis, alcohol in solvent, and this is the phenobarbital concentration. This is an example of co-solvents. You can see here, the more we are increasing the solvent composition, alcohol, the more is the solubility of phenobarbital. So this is the impact of co-solvency. And what about the impact of solvent pH on ionization behavior of drug? So if we are talking about a weak electrolyte, like poorly acidic or poorly basic drug, depending upon the pH of the water, it may behave like a strong electrolyte or a non-electrolyte. Okay, so when, hello,
Yes, sir.
we are
Yes, sir.
talking about a weakly acidic drug at all pH below than that of the acidic pKa of that drug, pKa, I think you know about pKa, that solute will stay in unionized phase and its solubility will be very low. And beyond that pKa value, its solubility will be high because the solute will be in ionized state. So it has a strong significance for gastrointestinal tract dependent solubility of a drug. So in our stomach, what is the average pH? It is 1.2. And in our intestine, what is the average pH? It is 6.8. So if we are talking about a weakly acidic drug, it will be not be dissolved in stomach, but when it will come in the intestine, it will be ionized and it will be easily dissolved in the liquid and it will be absorbed. Because for gastrointestinal absorption, I will teach you about these concepts in your biopharmaceutics module. A complete solubilization is important. Drug can be only absorbed in solubilized form, in a dissolved form. Okay, so this is the case where we need some attention. And for a weakly basic drug, it will have a strongly basic pKa value, and above that pKa value, at all pHs, it will show a low solubility. But below that pKa value, at all pHs, it will be staying in ionized form and it will show strong solubility, high solubility. Okay, this is the case for weakly basic drugs in gastrointestinal absorption phenomena. It will be dissolved in the stomach, but when it will come in intestine, due to high pH, again its solubility will be lower and it will show some precipitation, gastrointestinal precipitation. Okay, so any doubt? Is it clear? Okay, now I can recall your names. Piyojit Khan, is it clear?
Sir, পুরোটা না আবছা আবছা
একটা वीकली एसिडिक ड्रग যখন নিচ্ছ, जब तुम कोई वीकली एसिडिक ड्रग ले रहे हो, उसका पीके वैल्यू रहेगा. ओके, एसिडिक पीके वैल्यू, तुम पीएच समझते हो ना, तो
यस सर।
एक्वा सोल्यूशन का जो पीएच वैल्यू उसका जो एसिडिक पीके है उसका नीचे रहेगा, वहां पे अनआयोनाइज्ड रहेगा, और अनआयोनाइज्ड ड्रग का सॉल्युबिलिटी कम होता है। जो पीके वैल्यू है उसका ऊपर जितना पीएच रहेगा वहां पे वो आयोनाइज्ड होगा, तो आयोनाइज्ड ड्रग का सॉल्युबिलिटी ज्यादा होता है। So this is the reason why the impact of solvent pH plays important role in deciding ionization behavior and resultant solubility of the drug. Similarly, if we talk about weakly basic drug, at acidic pH below its pKa values, it will be in ionized form. So its solubility will be higher, but at all the pHs above than that of its pKa value, that is basic pH, its solubility will be lower because of unionized form, lack of ionization. Is it clear, Piyojit?
यस सर, यस सर।
Okay. So now we will know about ideal solutions. This is the last topic of today's class, and I will tell you to solve some mathematics at the end. So, ideal solution. So, what is ideal solution? Ideal solution is something where no change in the properties of the components other than dilution upon mixing take place. So here you are taking component A, you are taking component B, you are mixing it, and the enthalpy, resultant enthalpy of mixing will be 0, resulting volume change on mixing will be 0. This is ideal solution. This is something ideal, and ideal things never happens in our reality. ये कली युग है भाई, यहाँ पे ideal चीज होता नहीं है। तो real solution is basically persist, something what basically persist in reality, but this is ideality. Okay. The constructive properties, constitutive properties, for example, the vapor pressure, refractive index, surface tension, viscosity of the solution, or the weighted average of the properties of the pure individual constituents. Okay. So in a molecular perspective, ideality in a gas implies the complete absence of attractive forces, and ideality in a solution means completely uniformity of attractive forces. So these are important. If we talk about ideality in a gas, okay, it is known as, it is basically characterized by complete absence of attractive forces. No attractive force is there. Okay, every molecule stays its single existence, identical existence, or distinct existence. But when we are talking about ideality in a solution, solution is a liquid phase and it's a very condensed phase. Here absence of any attractive force is a unscientific phenomenon. So here an uniformity will of attractive force will exist. So what is called uniformity of attractive force? I have already told you about AA, BB and AB. So the value or magnitude of AA will be equal to BB. What will be equal to AB? So all cohesive or adhesive force of interaction among solute molecules or solvent molecules, or among maybe solute and solvent molecules, will be equal. That is called complete uniformity of attractive forces. For your information, when a liquid is present in the ideal state, then only we can use the term concentration. Okay. Okay, but in reality, when a real state exists, we can't use the word concentration from a thermodynamic perspective. The concentration term will be replaced by a term what is called activity there. Okay, similarly, we can use the term concentration for gaseous state only when we are talking about an ideal mixture. When we deviate from ideality, that is reality, in that case, the term concentration will be replaced by another term what is called fugacity for gaseous state. Okay, and there are some terms what is called activity coefficient or fugacity coefficient, what basically links these two terms, concentration with activity, concentration with fugacity. Okay, so let us come to Raoult's law. So just go through the statement. In an ideal solution, the partial vapor pressure of each volatile constituent is equal to the vapor pressure of the pure constituent multiplied by its mole fraction in the solution. Thus, for two constituents A and B, rho A, that is the partial vapor pressure of component A, will be equal to rho A naught. So what is rho A naught? It is the vapor pressure of pure component A multiplied by XA. XA is the mole fraction of A, and rho B is the partial vapor pressure of component B. What is equal to the rho B naught? What is rho B naught? It is the vapor pressure of pure component B multiplied by its mole fraction. Okay, so this is Raoult's law. So there is a mathematics. You will solve it. Just take a snap. It is your homework. In the next day, you will tell me about the result. It's based on Raoult's law. Hello, am I audible?
Yes, sir. Yes,
Yes,
sir.
sir.
सबको समझ में आ गया? राउट्स लॉ समझ में आ जाएगा यार, क्लास 12 से पढ़ रहे हो. आइडियलिटी रियलिटी समझ में आ गया, एक्टिविटी फुगासिटी कंसंट्रेशन, ठीक है?
Yes, sir.
This is a plot. Here you can see here. This x-axis, this is concentration. This is representing the vapor pressure plot of a binary mixture of benzene and ethylene chloride. Here you can see here benzene's concentration is 0, and gradually we are increasing. Sorry, here benzene's concentration or mole fraction is 1. Okay, and ethylene chloride's mole fraction is 0. So the more we are increasing the mole fraction of ethylene chloride, the partial vapor pressure of ethylene chloride is getting increased. And the reverse is true. If we see from this side, the more we are increasing concentration of benzene, the partial vapor pressure of benzene is that binary mixture is also getting increased, and this is the total vapor pressure. This is ideal condition. So what happens in reality? Let's see in the next slide. So this is nothing but a dilemma between the miscibility and ideality. So real solutions is something what deviates from Raoult's law. We are talking about liquid state. So we will restrict our discussion in the liquid state only. But the same phenomena can also take place for gaseous state as well as solid state also. Okay, but Raoult's law is applicable to only liquid state. So what happens in real solution? Basically, the solution or system deviates from Raoult's law, and there are two kinds of deviation. One is called negative deviation, another one is called positive deviation. So when negative deviation takes place, when the adhesive interaction between the molecules of different species exceeds the cohesive attraction between the like molecules, the vapor pressure of the solute is less than that expected from Raoult's ideal solution law, and negative deviation takes place. So this is a pictorial representation. This should be the ideal vapor pressure of the resultant binary mixture, but in reality, what is taking place? The value of the vapor pressure is just getting lower than that of the calculated from Raoult's law. Okay, so it is basically taking place when the adhesive force of interaction, that is AB, it is becoming higher in comparison to cohesive force of interaction between the like molecules like AA and BB. Okay, so an example is chloroform acetone. This is the pictorial representation. Here is a strong hydrogen bond between the chloroform and acetone, what basically exceeds the adhesive force of interaction rather than cohesive. Okay, and the reverse phenomena is positive deviation from Raoult's law. So when the interactions between A and B molecule is less than that between molecules of the pure constituents. So where cohesive force of interaction is the winning team. In that case, a positive deviation takes place. And here the value of the resultant total vapor pressure will be much more higher in comparison to the ideal vapor pressure, what we can calculate from Raoult's law. Here you can see from the pictorial representation, this is the real vapor pressure plot. What is much more higher from that dashed line? What is the ideal calculated vapor pressure? Okay, so what are the examples? Benzene, ethanol, chloroform ethanol. You have to remember the examples. This is important. So this is another concept. Does Raoult's law applicable to non-ideal solutions also? Because just sometimes ago we have told that Raoult's law is applicable to ideal solution and real solutions does not obey Raoult's law. So how can we calculate different thermodynamic phenomena as well as solution dependent vapor pressure for non-ideal solutions by using Raoult's law? Yes, Raoult's law is applicable to non-ideal solutions only at the extremities. So when you are talking about a binary mixture where a composition of a particular solute, particular component in the binary mixture is very low or very high, in that case only you can apply Raoult's law for calculation of non-ideal solutions also. Like if you are taking a chloroform ethanol mixture, chloroform is 5%, ethanol is 95%, then the vapor pressure of ethanol will be driven by Raoult's law. Okay, but when it will come to 50-50 concentration, then Raoult's law will not apply. And the opposite extremity will also be true. Like when ethanol is 5% and chloroform is 95%, then also will define the vapor pressure phenomena of chloroform. What is present at 95% phenomena? Okay, 95% concentration. So that's all about solution. And there are some mathematics, you will solve it. Just take a snap. This is your homework. Take a snap of these formulas. Take a snap of these phenomena. And take a snap of this homework. So you have to do 3 calculations and you have to provide the answers to me in the next class. I think all of you have taken the snap. So thank you very much. If you are having any doubt, please share. Hello.
Yes, sir.
Any doubt?
No, sir.
Okay. Have you taken the snaps?
Yes, sir.
Great, great. Share with your colleagues. So if you are not having any doubt, we will terminate our class here. Thank you. We will meet in the next class.
Thank you, sir.
Thank you all.